And after showing this picture of the wind turbines 4 times, I finally get to discuss the wind turbines. Let me just make a quick summary of what we've just gone over, because there were some important things there that we sort of hit in the examples, in the applications, right? So the energy equation we were happy with, and we checked all our signs and everything. In terms of fluid head, we wrote it as P1 plus V1 squared over 2G plus Z1 plus pump head is equal to P2 over gamma plus V2 squared over 2G. I'm not writing here the kinetic energy correction. That would only add little alphas here next to the velocity, but I'm not writing it right now. Z2 plus turbine head and plus head losses. So this was our full energy equation. Then we looked at the pump example, and we also had the pump power equation. So I want to write this, I want to emphasize that so that you have it clearly there and not sort of embedded in the example that we just did. So the power of the pump is equal to m dot G and pump head, or we also wrote it as gamma Q pump head. And then for a turbine, similar, turbine power equation. The turbine power equals m dot G turbine head, or gamma Q turbine head. But also we need to take into account that both a pump and turbine could have losses due to factors that are, the mechanical friction in the devices and so on. So for example, the pump power is actually the amount of power, the amount of work that the pump needs to deliver to the fluid. But if we want to calculate how much energy it's drawing from the grid, we need to take the efficiency into consideration. Similarly for the turbine, the amount of power we have in this equation is how much the power that the fluid gives to the turbine, but how much the turbine gives to the grid is compounded by the efficiencies there. So this is the power that the fluid gives to the turbine, right? So what the turbine gives to the grid as electricity is less than that because of the friction in the machine itself. And the same for the pump, but the other way around. Yes. The grid, the electricity grid, the high voltage wires that carry electricity to, the electricity grid. That's what I mean. Actual. Okay. So the efficiency is, and for both pump and turbine, it works the same. Power output divided by power input. That's the summary of what we did with all the previous examples, right? So now let me just take a couple of seconds. I see some people still taking notes, but what we're going to do next is a final application of the energy equation for the case of wind energy. And we're going to do it through an example that was actually part also of the midterm exam of fall 2009. This was problem number 4 of that midterm. I've abbreviated it a little bit from how it was, described in the exam, but it's the exam problem. So we consider wind turbine, like shown in the sketch here, and the turbine rotor has a diameter of 40 meters. The upstream wind velocity is 10 meters per second, the wind coming into a wind farm, say. And downstream of the turbine, the wind speed is 7 meters per second. And we're asked to calculate the power extracted from the wind turbine. And we're given a little tip here without proof that you can use to obtain the velocity. Here, v, as you can see, is the wind speed through the rotor on our picture. So we have v1, undisturbed, v through the rotor, and v2 downstream. And we're given this, okay? Then we're given another tip. In fact, use the continuity equation to express the mass flow rate in terms of v. So let's take the tip first. I'll start with that and write continuity. Well, it's simply, here we sort of imagine that, well, it's already drawn for us, a control volume here, and we have the mass going in and the mass going out. So we have rho A1 V1 equals rho A2 V2, our simplest form of the continuity equation for steady 1D flow. But the tip says write it in terms of V. So obviously the mass here in the middle is also the same, but the area is different, it's given as A, and the velocity is different and it's given as V. So we're going to use that. Now we're going to use the energy equation. So for the energy equation we see, okay, Z1, there's no change in elevation. We're going to assume Z1 is equal to Z2. No change in elevation. Pressure is atmospheric everywhere. P1 equals P2 equals just atmospheric pressure, so it will cancel out of our energy equation. So the only terms we have in the energy equation are the velocity terms, the head, but we have no pump, and well, nowhere in this problem are we told that we need to consider any losses, so we're not going to consider the losses here for the time being. So we just have the velocity terms and the turbine head, basically. All of the other terms in the energy equation cancel out. We just wrote the energy equation in the previous slide, so we can immediately write it in the simplified form for this problem, right? For the inlet, pressure 1 is gone, Z1 is gone, we only have V1 squared over 2G. No pump, so for the outlet we have V2 squared over 2G, pressure 2 is gone, Z2 is gone, and the turbine head. And we're not considering losses here. So right away we have the turbine head is equal to, let's not make a mistake with the signs, V1 squared minus V2 squared over 2G. And it turns out that we have all those things because velocity upstream is 10 meters per second, velocity downstream is 7 meters per second, we have all of that, and G. So we can calculate this. HT is equal to, what is V1? 10 meters per second minus 7 meters per second, all squared, these two guys squared, divided by 2 and times 9.8 meters second squared. So we can put all that in our calculator and obtain the turbine head, 2.6 meters. So what now? See? The power equation, very good. We just learned to use the power equation, and we need to be able to write that down and see if we have everything. So for the power equation we have W dot equals, let's write it as gamma QHT, and well, we can calculate Q because we have area velocity and rho. Well, rho's in here. So let's write it as rho G, and this is just AV and the turbine head. So now the area we can calculate. We can use, oh, here we can use the tip for V. So let's do that right here. We can calculate 1/2. V1 is given us 10, V2 is given us 7, so 17 divided by 2 is 8.5. So we have velocity, 8.5, the area over here with this diameter pi over 4 d squared. We have that. We have g, we have rho, we have everything. Right? So I didn't leave any space. Yes, question? Just air. Yes, just air. It's a wind turbine. So just air coming in, and we've drawn a control volume here that follows that streamline from the upstream point to the tip of the rotor to the downstream point of that particular fluid particle. Yes?
So WT is the work that the air
Here.
is on the turbine that was given on.
Yes. So the turbine is rotating and extracting. That rotation is the product of its interaction with the fluid, and it's extracting some power from the fluid. That is what has slowed the fluid down. So the fluid has less kinetic energy. That's why it goes from a velocity of 10 meters per second to 7 meters per second. And that change in kinetic energy in the fluid is turned into a shaft that rotates, and somewhere down in the system that rotation is turned into electricity. That's just as simple as the same as the case for a water turbine, and here we're just using air. Yeah, we good? So let's see if that disappears in my picture. Oh, that disappears. So let me just use the space that I cleared up with my picture disappearing to write the final answer, so that you have it, the problem complete. W dot at the turbine is equal to, so I'm going to put all the numbers here for rho, G, A, V, and HT. We have them. Rho of air. Suppose I have my book and my tables and I can look this up, or I have it memorized. 1.2 kilograms per cubic meter for air at atmospheric conditions. G, 9.8 meters per second squared. The area, and pi over 4, and we were given 40 meters diameter rotor, so that's the area. The velocity we just calculated with the tip that was given here, 8.5. I don't want to confuse you with a little dot here. I'm just going to put a parenthesis. Meters per second is our velocity, and the turbine head, we just calculated that, 2.6 meters. Oops, meters. So now we have all these numbers punched into the calculator, and I got, you can check my math, my arithmetic afterwards, 326 kilowatt is what I obtained. And that was the problem in the exam. You just had to apply continuity, follow the instructions, the tips, and energy equation. We're going to go one step further now. So the power, the coefficient of performance, which we can write Cp, is defined as the power extracted from the turbine divided by the power available in the wind. So the turbine extracts an amount of power from the wind, and we've already calculated that. But how much power was already available in the wind? Basically, the full kinetic energy of the power, if it had gone to full stop, that is how much energy was there, right? But it didn't go to full stop. It went from 10 meters per second to 7 meters per second. So the available power, and this I'm also going to give to you without proof, the power available in the wind, because just in the interest of time, I'm just going to give you this, flowing across an area A at velocity v is equal to 1/2 rho V cubed times A. So in the example that we just did, in the exercise, we had area equals pi fourth 40 meters squared, and I can calculate that. It gives me, I think, if I understand correctly my messy notes, 1,256.6 cubic meters. The velocity, if there was no turbine over there, the wind passing through that area would be passing with its unperturbed velocity, correct? So this is the power available in the wind passing through that area if there was no turbine there. So that velocity is 10 meters per second, the unperturbed wind velocity. So we can calculate the power in the wind for this case, and it's 1/2 rho, 1.2 kilograms per cubic meter, 1,256.6 meters squared. I made a mistake here. It's a square in my units. It's a typo. Trying to write and talk at the same time. Squared. And 10 meters per second. For my equation, it's cubed. If I was careful, I would actually work out all of these units and make sure that they make sense and they give me the correct units, but I will skip that at this point in the interest of time and give you the result is 754 kilowatt. But please, in your own time, when you review your notes, check your units once more. It never hurts to. So this means that if I calculate this coefficient of performance for this case, Cp, it is equal to what we obtained in the problem was 326 divided by 754. It gives me 0.43. So it's a 43% efficiency. You agree? Now, it seems a little low, doesn't it? Is for this case that we've given the numbers, okay? We're giving the numbers. It does look a little small, doesn't it, to you? Does it look a little small to you? Yes. It has a combination of two things. We will see it in a moment. If you give me a moment, I will explain something, which is, well, let me just say it. This seems a little low, but in fact, there is a limit, and I will show you how to obtain that. There is a limit to how much power it is possible to extract from the wind. If I just wave my hands at that problem, let me explain it this way. The wind, when it's going through the turbine, cannot really stop dead to zero, right? So for that reason, you intuitively understand that we can't take all of the energy from it, right? Does it make sense? So there is a limit. There's a physical limit to what even a perfect turbine could take. This turbine takes 43%, which doesn't seem like too much, but how does it compare to that limit is the question that we need to answer. So I'll show you how to calculate that limit in a moment. Yes? That's what we're going to, that limit is the Betz limit. Yes, this one here. There's a limit to how much power. You guys already know about this. A wind turbine can extract from the wind. Let's see if I can do this in the next few minutes, and you'll believe it and see that it's this turbine. Did you see some People writing down. Let me see if I can. Okay. Yeah. So let me see. I didn't leave any space for that in my slide. So let me just use the same one.
Extracted by the have an efficiency of 1, then your coefficient
No, it's actually the coefficient of performance that we just got is a little lower than the actual physical limit that we're going to obtain now. So already the design of the turbine was somehow incorporated in those numbers that we were given in the problem. The fact that a turbine of 4 meters diameter took the wind from 10 meters per second to 7 meters per second, there was an efficiency already included in those numbers. Now we're going to see that how this number that we just got, the 43%, compares with this limit. So let's consider now, again, the example that we just had. We wrote down continuity, and for continuity we had rho A1 V1 equals rho A2 V2 equals rho AV. We wrote down energy, but let me write it in a different form now. The energy equation, I'm going to write it as m dot. So basically I've multiplied the whole equation by m dot. V1 squared over 2 equals m dot V2 squared over 2 plus W dot. So this is now the power. So the power, I'm going to use a big P now for power. I hope you're not confused. Well, let me write big P equals W dot equals M dot times 1/2. And let me make sure that I don't make a mistake. V1 squared minus V2 squared. Okay. Now we're going to use the fact here that V is equal to 1/2 V1 plus V2. It was given in the other problem. And we write P equals 1/2. So we have M dot. For M dot, I'm going to write rho A V. But for V, I'm going to write this. So 1/2 V1 plus V2. And I still have this term over here. V1 squared minus V2 squared. Yes? Good. Okay. So I can multiply that out. And I have 1/4 rho A. And I'm going to multiply these things here. V1 cubed plus V1 V2 squared minus V1. I'm checking here with my notes to make sure that I don't have to do the calculations in my head while writing. Minus V2 cubed, the last term. And if I want to calculate the CP, I need to write this power here divided by the maximum power in the wind, which is already, I told you previously that it was 1/2 rho A V1 cubed. Yes? No? You have a question? Yes. Thank you. Even when I'm trying to copy my notes, writing and at the same, so this one is V1, okay, so V1 squared V2. Thank you for checking my result. Thank you. Now it's good? So now I'm going to divide over by all these things. The 1/2 simplifies to, the 1/4 simplifies to 1/2. Rho and A cancel out. Right, so I have 1/2 left. And I divide by V1 cubed. So V1 cubed divided by V1 cubed is just 1. Plus, was my signs correct? Yes. divided by V1 cubed, I have simply V2 over V1. Then I have V2 over V1 squared minus V2 over V1 cubed. So if we find the maximum of this, one way to do this is to take the derivatives with respect to V2 over V1 and make that equal to 0. It's just a polynomial with respect to that, so it makes it easier. I'm going to take the derivative with respect to that. So dCp with respect to V2 over V1 is equal to 1/2. The first term is constant, so the derivative of that is 0. Second term, just 1, minus 2. V2 over V1, this is just polynomial terms, minus 3. V2 over V1 squared. And I'm going to make this equal to 0 to find the maximum. So since I'm running out of space, I'm going to do it over here. I'm going to rewrite that as, I can factor it out as 1 plus V2 over V1 and 1 minus 3. And I'm trying to rush a little bit here, forgive me, just to give Professor Wroblewski his 5 minutes that he wanted with you. And the only positive root of this is V2 over V1 equals to 1/3. Negative root of this equation doesn't have a physical meaning. So we put this back into this one over here, and we get that CP maximum is equal to, I'm going to skip the calculations and just give you the result, 16 over 27, which is equal to 0.59 or 59.3. This is the maximum possible coefficient of performance, the maximum fraction of the wind that can be extracted by a wind turbine. It's a physical maximum. And so now when we go back to our problem where the coefficient of performance was 43%, we kind of have to compare it with that. 43% is not as far from 59 as we thought. This is the Betz limit that you were mentioning precisely, the maximum amount of power available in the wind. I mean, the reason for this limit basically is since the fluid is going to the turbine and needs to slow down on the other side of the turbine, you see that basically the area for conservation of mass, if you consider a stream tube, has to get bigger, right? And so because the area has to get bigger, if you go forward in front of the turbine, the area, actually the actual amount of wind that the turbine is able to capture is smaller than the area of the full span of the rotor. The other way around. The inlet is smaller than the outlet because the fluid needs to slow down. So for conservation of mass, the area must be bigger. And so in front of the amount of wind that the turbine can catch basically is a smaller area than its own span. Does that make sense? So.
Makes sense.
Okay, so let me give now Professor Wroblewski let me give the class to Professor Wroblewski so he can tell you more about this.